This is part one of the gyroscopic precession section of our aeronautical engineering course. The rotor of a helicopter is a good illustration of gyroscopic precession. Let's say we're looking down at a helicopter as if we're parachuting above it or something like that. And there it's facing toward the north, there's the east, there's the west, the tail of it's toward the south. Okay, and let's say the rotor is spinning clockwise. Okay, there we go, going around that way. Okay, as seen from our position above the helicopter, a swash plate at the center between the rotors changes each rotor's angle of attack. Let's pretend that this potato salad lid and this oatmeal can lid are two parts of a swash plate. A swash plate has two parts, one of which is stationary, or at least stationary with respect to the rest of the helicopter, and the top part, it spins around as the rotors spin around and round. Okay, the swash plate can lean to the left, to the west like that, or to the right, to the east, or toward the north, or toward the south, or in any direction. The control stick in the pilot's right hand is called the cyclic stick. It controls what direction this swash plate leans in. And the stick in his left hand over here is called the collective. It makes the whole swash plate go up or down. Let's say the swash plate is lifted higher over here on the east side of it, and consequently lower on the west side, but the north and south, they're at average height. Okay, so it can lean down, north, down, south, down to the west, down to the east, but right now we're going to say it's higher on the east side. Okay, so when the rotors spin around, when the rotor's over here on the east side, it has its greatest angle of attack. When the rotor is over here on the west side, it has its minimum angle of attack. When the rotor is toward the north or toward the south, it has an average angle of attack. So you would think that since the greatest angle of attack when the rotor is over here on the east side, that the rotor would lift up when it's over on the east side and go down on the west side, and that the helicopter would move toward the west. But that's not the way it works. With a gyroscope, when you put a force over here, which we're doing by having a greater angle of attack when the rotor is over to the east, it has more lift when it's over here to the east than it has when it's to the south or the west or the north. With a gyroscope, pressing up over here to the east with the rotor spinning clockwise makes the rotor rise when it's facing south. So it leans forward and it swings down low when it's in the north, so the plane of this rotor is tilted that way toward the north, which makes the helicopter go forward. So the lesson to be learned is that if you push up on a rotating body, it rises up 90 degrees or 1/4 of a circle past the place where it is pushed up. In other words, our helicopter rotor, which is pushed up more when it is on the right, on the east side of our helicopter, because of the high angle of attack, rises to its highest position when it is behind the helicopter. When the rotor is swinging on the left, west side of the helicopter, where its angle of attack is minimum, the rotor is not being pushed up as much as it is at every other position. So the rotor swings to its lowest point when it is in the front or north of the helicopter. Airplane pilots are taught about gyroscopic precession because pressing the rudder pedals, which causes the airplane to turn to the left or the right. So if we mash the right rudder, the airplane will do like that. Left rudder does like that. Okay, this results in gyroscopic precession of the propeller, which makes the plane pitch up or down, depending on whether you mash the right or left rudder. Okay, conversely, pulling back or pushing forward on the yoke, which makes the airplane pitch up or down. Okay, if we push our yoke forward, that means the elevator back here is leaned down, which makes the nose pitch down. So conversely, pulling back or pushing forward on the yoke, which makes the airplane change its pitch up or down, results in gyroscopic precession, which makes the plane turn right or left. So using the controls of an airplane to change the pitch of the airplane causes gyroscopic precession that turns the airplane's nose left or right, and using the controls of an airplane to turn the nose of the airplane left or right causes gyroscopic precession that changes the airplane's pitch. The propeller of a Cessna 150 turns clockwise. So let's see, it's kind of like this. If you're looking at it from behind the airplane, see, here's the top of it going down on the right side, swinging by the bottom, coming up on the left side. Okay. When the airplane is taking off, accelerating down the runway, and the pilot pulls back on the yoke, or it's a yoke on a Cessna 150, wouldn't be a stick. Okay, the airplane pitches up, so he's running down the runway real fast, pulls back on the yoke, that makes the elevator go up, which pushes down on the tail, which lifts the nose. Okay, and the airplane pitches up. So this maneuver is comparable to pulling the top blade of the propeller. See here, when the propeller is up here, when you cause the plane to pitch up, that's just like pushing on the top blade of the propeller toward the back of the plane and pulling the bottom blade of the propeller forward. Okay, because forces on a rotating body result in a change of the body's position 90 degrees or 1/4 of a circle past where the force is applied, the propeller blades will tend to go forward when they are swinging up on the left side and backward when they're swinging down on the right side. Okay, I'm pushing forward here because I'm pitching it up. The propeller shaft is causing the plane of rotation to change. It's causing the top part to go backwards, the bottom part to go forward. But since this blade is going around this way, pushing on it while it's up here makes it go back when it's over here on the right side of the plane, which makes the airplane turn to the right. And consequently, if the pilot is flying straight and level and he pushes forward on the yoke, causing the airplane to pitch down, the gyroscopic precession will cause the airplane to turn to the left. We're on the back porch of the Hodgepodge Lodge with a collapsed pool roof in our background. That ought to make you trust in everything I've taught you about structural design, shouldn't it? Notice this bicycle wheel, it's got a rope tied to one side of one end of the axle, and it just hangs there like that. The center of gravity is in line with the rope, but if you spin the wheel, it seems to defy gravity. See there, and if I lift the same with my right hand that the rope is lifting, then the wheel doesn't go anywhere. But if I let go, it precesses clockwise looking down on it. If I lift more over here so that the rope is not lifting, it precesses in the other direction. Let's speed it up a little more. Okay, and let's say I push this side that way and pull this side this way. That makes top of it go over toward the rope. If I do the opposite, it makes top go away from the rope. Okay. pulling up on that end of the axle puts a gyroscopic torque on this, so it's essentially like pushing this part of the wheel that way and pulling that part of the wheel that way. But pushing that part that way doesn't make that part go that way. It makes it go that way when it's over here, 90 degrees from there. So the things you need to remember about this lesson are that when you pull up on this part, that's like pushing over here, which makes a position change here, so it precesses that way. Pull up on this part, does just the opposite. And when you push sideways on these, notice how the top and bottom lean over. Okay. When I push this way, it's like pushing this that way, but since it's going around this way, it makes the bottom go over that way. And another thing to remember is that the faster it is rotating, on its axis this way, the slower it precesses around this way. Notice as it slows down with its rotation around its axis, it will precess at a faster rate. An airplane pilot needs to know how applying a force to the axis, or changing the axis of a rotating body, causes that rotating body's plane to change. In other words, when he pitches the plane up and down, how it's going to make it turn right or left, and when he noses it right and left, how that's going to make it pitch up or down. Okay, that's what a pilot needs to know, but an aeronautical engineer needs to know how much force is involved here, so he can make sure that propeller shaft is big enough and heavy duty enough to do the job. Okay, if you jack up the front wheel of a car off the ground, here's a car wheel, here's a bicycle wheel, and let's say they have the same diameter, but obviously the car wheel is going to be much more massive than the bicycle wheel, or it's going to weigh more, same thing almost. Okay, and let's say you spin them both around, well, you're going to have to push harder on the car wheel to get it started spinning, and you'll have to apply more force to slow it down to stop it from spinning. It has more angular momentum. But that's about enough for this lesson. We'll talk about angular momentum in part 2 of gyroscopic precession.